Ora vediamo un attimo. Allora, questa qua va bene, ok. Ok, siamo nel corso in lingua inglese, ho appena fatto lezione dall'altra parte, scusate. Ok, can you hear me without the microphone? Ok. So sorry. Okay, so can you hear me, online students?
Yes.
Thanks. Let me share my screen. This one. Okay. Okay, we started last week the first order linear equations, differential equations with constant coefficients, and we derived the general solution formula and a particular solution formula. If you remember, we derived the general solution formula by means of a change of variable, okay? So we reduced our equation to one that corresponds to the basic model of constant growth, except that the new variable was the difference between the original variable and its steady state level, okay? So basically we derived the solution formula in general, the general solution formula, and we discussed the constant corresponding to a given initial condition, so a given initial value of the variable. I want only to recap what the general solution formula is. The general solution formula is this one: x at time t is an arbitrary multiplicative constant times the exponential of minus at plus b over a. Now remember that this formula corresponds to a linear differential equation with constant coefficient displayed like this, x dot plus ax equal to b. So a is the coefficient of x on the left-hand side when we write the equation in this way, and b is the constant on the right-hand side, okay? This quantity b over a is the steady-state solution to the equation, x star equal to b over a. And the coefficient that multiplies the t at the exponent is minus a, where a is this coefficient. Okay? It is more interesting to rewrite the solution in terms not of an arbitrary generic constant c, but transform this part by computing a particular solution. That is, if we want that this at the initial time is x0, which is a parameter, a number, then we realize immediately that our arbitrary constant c here is just the initial deviation of our variable from its steady state level, okay? So basically, what I'm going to do today is first to show you a few more examples of this basic case. Next, to extend the case to a situation in which b is not constant but changes in two very simple cases. It is a linear function of time or it is an exponential function of time. The second one is easier. There are two solution methods for each of these cases, and I will show you both, but I would like to do that by examples because you already have all the slides with the theory, so I will show you all these particular cases by examples. And but before doing that, I want to go back again to the original equation, the introductory equation that we solved. It was x dot plus 1 over 4x, where is the pen? It's here, equal to 2, okay? I want to show you a lot of different things that are already written in the slide, so you don't need to write them, okay? Again, just try to catch the main message here. Matrices is not for you today. Okay, so x dot plus 1 over 4x was equal to 2. Let me recap the main messages, okay? We know that the general solution formula to this is c times exponential minus 1 over 4t. You see 1 over 4 has become minus 1 over 4 plus 8. This 8, now you have the general model, x dot plus ax is equal to b. The general solution formula is c exponential minus at. Okay, it is exactly this case, more general, plus a is b over a. The 8 is b over a, okay? 2 divided by 1/4, 2 times 4. So this is called x star, because it is the steady state constant solution to the differential equation. This is an arbitrary constant. Now, if I apply the initial condition that x at time 0, well, this is x at time t, in general, a family of solutions, because it is an integral. Solving a differential equations means basically finding integrals, because we start from derivatives, right? So x0, we want this to be equal to a specified value, we leave it as a parameter here. We don't specify 10, 12, okay, 2. It's x0. So what is x at time 0? It's c plus b over a. This is imposing the initial condition, and this comes from replacing 0 to t here. This means that our constant c is equal to x0 minus b over a, so it is equal to x0 minus x star. So it is the initial deviation from the steady state, okay? So our solution, this is written in a way which is mathematically correct, of course, but tells us nothing about the meaning of the constant c, okay? This is a more sensible way to write the solution. In fact, it is a particular solution, but it is left general because it is parametric, okay? It corresponds to a specified initial level x0. So the solution in this case is xt equal to x0 minus b over a, or x0 minus x star, times exponential minus at plus b over a, where b over a is our x star. What the main message here is, what is the solution in this particular case, in which we have a equal to 1/4 and b over a equal to 8. So in our case it is x0, sorry, xt is equal to x0 minus 8 times exponential minus 1/4t plus 8. And this is a very interesting interpretation to our solution, because it tells us a lot about the properties of the solution. For instance, what happens as t tends to plus infinity? We can just write infinity because it's clear that t time is a positive variable of xt. We would say it depends on two things. First, it depends on whether, in this case, the limit xt tends to plus infinity is clearly equal to 8 for any x0. We can state this because the initial deviation from the steady state is multiplied by a factor that becomes smaller and smaller for larger t. Okay? As t increases, this factor tends to 0. The initial deviation from the steady state tends to 0. What is left in the long run is the steady state level of the variable. So basically, the graphical representation to our solution here is 8 is the level here, x star is equal to 8. Here is t. If we start from x0 here, x0 minus 8 is this negative quantity. But this negative quantity becomes small, this negative deviation becomes smaller and smaller over time. Okay? If x0 is here, a very large positive initial deviation, okay, we start here, but in the long run, this part disappears. What is the main feature that makes that causes this long-run outcome? The main feature is the fact that this coefficient is minus 1/4t. So the main feature is that parameter a in the original equation that appears here is positive, okay? If it is positive, it appears with a negative sign in the solution, and this is what makes this term disappear in the long run, okay? So A positive, as is in our case, the steady state x star is globally stable. everything is written in the slides, okay? So all these definitions. Globally stable means that the limit as t tends to infinity of the solution is equal to 8, in our case x star is equal to 8, right? Is equal to x star for any initial level of the variable, globally. Globally means for any initial level of the variable. Because there are some cases, not for linear equations, but for other types of equations, there are some cases in which it is stable but only locally. So not for all initial levels of the variable, but only for initial levels of the variable that are sufficiently close to the steady state level, okay? Otherwise, there may be some other outcome in the long run. And this is a very important property of nonlinear systems. The fact that stability is not in general global, it is only local. Okay, so this is the first insight, okay? So now look at this equation, x dot minus 1 over 4 x is equal to minus 2. Okay? The steady state is again given by minus 2 divided by minus 1, 4. Okay? B over A. B over A. Which is again equal to 8. But if we write down the general solution to this one, we get that xt is equal to c times the exponential of 1 over 4t, again plus 8. Now things work very different from the previous case because this is positive, okay? So the initial deviation from the steady state, again, if you want to impose an initial condition, you get that c plus 8 must be equal to x0, and again you have that c is equal to x0 minus 8, okay? So this c is x0 minus 8. C is x0 minus 8. So the point here is that the solution works in this way. We have 8 here. You can start even very close to the steady state, very small initial deviation, but what happens to your deviation over time? It becomes amplified by this exponential growth, okay? So the solution works like this. If you start above, you will remain above, and far away as time increases, and if you start below, you will have something like this. So this is the basic idea. What is the feature that determines divergence in this case? The steady state is not stable in this case, okay? Sometimes we say unstable. It's not stable. You can start even so it is an equilibrium only in theory. In practice, it will never be reached by our system in practice, unless in one particular case, what is the particular case in which the system will be at the equilibrium in the long run? If it starts exactly at the equilibrium, because if it starts exactly at the equilibrium, it will remain there. Why? Look at the general solution. If x0 is equal to 8, okay, here we have a growing exponential factor, but it is multiplied by 0, so it is neutralized from the beginning, and the system will evolve at the constant level 8, which is the starting level. But what I want to point out is that, okay, this is a mathematical model. We see that the system can be, in principle, in equilibrium, if it starts exactly at the equilibrium. In practice, in applied models, it will never be at the equilibrium, because even a very small shock that happens at some point in time will move the point away from the equilibrium, and even a very small deviation will be amplified over time, okay? So there are no forces in this system, there are no forces that bring the system back to equilibrium. While here, we have a force that brings the system to the equilibrium, okay? So this is the main insight. Unstable systems do have a steady state in general, or more steady states, but they are practically not so important as they are in stable systems. Because in a stable system, a steady state is an outcome that can be reached in the long run, okay? If the system is unstable, in practice, the system will never be at a steady state. So this is the main message. So this is what we learn from linear differential equations. So the main insight is that this is the general solution. We can write the general solution as a particular solution in the sense that we change the constant, which is no longer C, it is the initial level of the variable. So the formula is different, like this. But in this case, we emphasize the initial deviation from the steady state. If A is positive, we have stability of the steady state, global stability. If A is negative, we have an unstable steady state. And any other system of this type is like this, okay? So there is no particular changes. I mean, everything is included in the solution formula in the general case. On another point that is useful for the next equation, next type of equation, we derive the solution formula by means of a change of variable. Now, I want to show you, this is already in the slides, but I want to show you another perspective on the solution formula, which is useful to solve also the models in which B is not constant, okay? So a slight change of perspective. This system is the constant growth model. Its general solution is xt is equal to c times exponential of minus at. Okay? This is the constant growth model. So basically, here we have the case b equal to 0. Now consider this, the system in which b is not equal to 0, x dot plus ax equal to b. Here b is different from 0. If we start from this one and then we consider this one, we say that this is the homogeneous system associated to our given system, which is not homogeneous. This is non-homogeneous. Non-homogeneous means that the right-hand side is not 0, okay? Homogeneous means that the right-hand side is 0. But if we start from this one, and we consider this one, we don't consider B, we consider 0, we are dealing with the homogeneous system associated to x dot plus ax equal to B, which is instead non-homogeneous, okay? Sometimes we say the associated homogeneous system. So you know what I mean, okay? Now, there is an important result that holds in a very general fashion for equations for systems, provided that they are linear, but not necessarily constant coefficients, time-varying coefficients, time-varying forcing term, time-varying everything, but linear systems, is that the solution is made up of two parts. Is A plus B, where A is the general solution. So we want to find the general solution to this linear system. General solution to a linear system of any type is made of two parts. A is the general solution to the associated homogeneous system. Sometimes very easy to find, because we have 0 here. And B is any, just to find one, with any possible method, any particular solution to the initial system, the non-homogeneous system. Look, this is a powerful result, and you will see an application later, because what we have to do, even if the system seems difficult, first of all, reduce the system to something which is much easier, which is the homogeneous one. Find the general solution to this one. Next, with any method, heuristic methods, trials and errors, any method, try to find just one particular solution to your full system. You have to solve the general solution to your system, okay? Just find one solution among the infinitely many, then take the sum of the general solution to the associated homogeneous system and your particular solution that you found heuristically, and you have the general solution to your initial non-homogeneous system, okay? This works also in this simple case, because what is the general solution to the homogeneous system? It is this one. So in our example, x dot plus ax equal to b, so suppress b, okay, consider 0, and you have that the general solution is c times exponential minus at. Find a particular solution, not the general solution, just one particular solution to your full system. What is the easiest particular solution to find? The constant solution, okay? In this particular case, we do have constant solutions. Find the constant solution, the steady state. Take the sum of the two parts, and you have the general solution to our system, okay? Which is that it is slightly more difficult to find, let's say, a particular solution to the system, okay? Here, it's easy because you can find a steady state. In a case in which b is not constant, for instance, instead of being 2, it's equal to 2 plus 1/2 t, we must be able to find a particular solution by a method which is called, it's a type of trial and error method, okay? It's called method of undetermined coefficients. You may know something about this method already. We find a particular solution, but the general solution, even if here we have bt, the general solution is, again, the solution to this one, okay? Which is this. So it's very easy to solve the system. I want to show you an example immediately, because we have two methods to solve this, and one is precisely based on this principle, this one, which is called superposition principle. So it's the superposition of two different solutions, okay? Now look at this example and how it is easy to solve this type of equations in which we have b, which is not constant but changes over time, okay? So suppose that we want to solve this system. S3 and 1, okay? x dot minus 1/2 x is equal to t minus 3. Okay. By the way, if t is 0, we have x dot minus 1/2 x is equal to minus 3, which is a linear system with constant coefficients, and we can solve it, okay? We want to find the general solution to this system, which is called, I denoted it with an asterisk, okay? In this way. First step, consider the system x dot minus 1/2 x is equal to 0. What is the general solution to this system? It is a constant growth model. xt, arbitrary constant c times exponential of what? 1/2 t. Okay? Now, second step, find a particular solution to the full system. Here we cannot find a steady state solution. There are no steady state solutions here. Can you realize why we cannot find steady state solutions here? Just look at how would you find a steady state here? Steady state is a constant solution. So we wonder whether there are constant solutions to this equation. Constant solutions have the time derivative equal to 0, so that would be equal to 0. So there must be a constant x such that minus 1/2 x is equal to t minus 3. X cannot be constant, okay? If you multiply, you solve for x, you get something that depends on t. There are no constant solutions here. So we have to find another type of solution. The point 2 is just a theoretical step in which we have to find a particular solution to our system. A very powerful heuristic method is this one. Search among solutions with structure linear, exactly as the quantity that appears at the right-hand side. Okay? So we mimic the quantity that appears at the right-hand side. This is t minus 3. We want to be general because next we want to do some fine-tuning of the parameters to find our solution, okay? But we want it to be linear. We are not sure that a linear particular solution exists, but we have a powerful tool to check whether it exists or not, and in case it exists, to find the coefficients. So we want solutions of the type x particular of t equal to alpha plus beta t. Okay, linear functions of time, an intercept and a slope, alpha plus beta t. Okay, so if a solution like this one exists, then its derivative, its time derivative, x dot p, would be equal to beta. Okay? We are not sure that a solution like this actually exists. But if it exists, its time derivative is equal to beta. Okay? Its time derivative would be equal to beta, and this would be the function. Now, remember that the differential equation, which is this one, relates at each point in time the derivative, the value of the function, and some other function of time. So if we replace here the derivative, which is this one, and if we replace here the function, which is this one, we must find t minus 3, okay? Because this must be equal to this in order for the function to satisfy the differential equation, so to be a solution to the differential equation. But by doing that, we have basically a condition on parameters a and b, which can be selected with specific numerical values such that our equality is valid, okay? So basically, this is what we do. X dot, which is beta. So we have to write this, okay? X dot plus or minus, minus 1/2 x equal to t minus 3. Okay, x dot is beta. Minus 1/2 x, the general family of our functions is alpha t plus beta. Okay? This must be equal to t minus 3. Now, here, we solve this, and we group the terms, which are numbers, with the terms that are coefficients of t. So we have beta minus 1/2 alpha. Sorry, here is alpha plus beta t, not alpha t plus beta, sorry. Alpha plus beta t. Alpha plus beta t. Okay? So beta minus 1/2 alpha minus beta over 2 times t, right? Now we have to find parameters beta and alpha to find a specific linear function that satisfies the equation. But this must be equal to t minus 3, and this means that minus beta over 2 must be equal to 1. Minus beta over 2 is the coefficient of t, and this must be equal to 1 in order for this to match this one, okay? So minus beta over 2 must be equal to 1. And the constant term must be equal to minus 3. So beta minus 1/2 alpha must be equal to minus 3. Are the conceptual steps clear? So this is called, I remember that I said something already about this method, which is called method of undetermined coefficients, okay? I know what or I guess what the structure of the solution should be, but I write down a family of functions containing parameters. Now, if my conjecture is true, so if this solution works, I can find the specific values of the parameters. And this means that if my particular solution that I want to find out really exists with a similar structure, then necessarily minus beta over 2 must be equal to 1, and beta minus 1/2 alpha must be equal to minus 3, necessarily. Because otherwise this is not a solution to our system. Now this is a simple system from which I obtain beta equal to minus 2. Next, this can be written as beta plus 3 is equal to, beta. Now I have to find alpha here. Okay, so 1 alpha is equal to beta plus 3. So alpha is equal to beta plus 3 times 2. Okay? So this is the second equation written in this way. If beta is equal to minus 2, alpha is minus 2 plus 3 is 1 times 2. It's 2. My conjecture was right. There exists a linear function of the type alpha plus beta t with alpha equal to 2 and beta equal to minus 2 that satisfies the differential equation. Okay? So my particular solution is equal to 2 minus 2t. Okay? This is only one particular solution among the infinitely many, but now I have my powerful step 3 of the superposition principle that says, okay, A plus B, the general solution to the homogeneous system plus your particular solution that you found with any heuristic method, okay? So the general solution to my system, which was x dot minus 1/2 x equal to t minus 3 is xt equal to c exponential 1/2 t plus this one, xp of t, 2 minus 2t. Okay? Now, what is the meaning of this? What happens? Here we don't have steady states. First of all, what is C? Okay? Because if we have a system with a constant B, we know what C is. It's the initial deviation of the system from the steady state. But here there is no steady state. There is no steady state here. So what is the meaning of C? In order to find the meaning of C, we have to impose x0 given, okay? We want x0 to be equal to x0 given. When x is equal to 0, this becomes C, this is 0, plus 2, C plus 2. This must be equal to x0, so C is equal to x0 minus 2. For the moment, don't worry about the meaning of this, but we can replace it here. So our solution corresponding to an initial condition, x0, is xt, now we can denote it in this way, equal to x0 minus 2, exponential 1/2 t minus 2t plus 2.
Sorry, why is 0 is c plus 2?
It's c plus 2 because when t is equal to 0, this becomes 1, this becomes 0. So what survives is only 2 here, okay? So, I mean, the initial condition, it means that I want to find the value of C corresponding to a given initial condition, and I found this solution. I would like to know what is the meaning of x0 minus 2. The meaning of x0 minus 2 is related to the meaning of this particular solution that we found with our heuristic, okay, method. This solution is a trajectory. It is a linear trajectory. It's one among the possible, infinitely many possible solutions, okay? It's a very simple trajectory. 2 minus 2t. When t is equal to 0, it starts from 2. So at time 0, this very particular solution that we found, that plays the role of the steady state, it's not a steady state because it is not constant, but it plays the role of a kind of long-run solution, starts from the level 2, which is precisely the level that appears here. If you want to get some geometric insight on this, which is useful to also to solve the exercises, just look at the graph of the solution. Solution to a non-autonomous equation. Here it is. Okay, this f of t in red is our solution that corresponds to a given x0. For instance, here x0 is equal to 3, but what happened? It is here, okay? And the green one is the very particular solution that we found. Both of them belong to the family of the infinitely many solutions, okay? Both of them. Now suppose that my x0 is not 3, it's 2.1. You see, it starts very close to 2. For a long time, it evolves very close to the green solution, okay? If it starts from 2.5, you see, it goes like this. So basically, this plays a little bit the role of an equilibrium solution, because if we start exactly there, so if x0 is equal to 2, there is a perfect superposition of the overlapping of the two curves. But if x0 is not 2, but it is above 2, for instance 3, like in the previous example, you get something like this. If it is 4, you get something like this. If it is 1, so it lies below, you have something like this, okay? So basically our particular solution that we found in this way plays somewhat the role of the steady state. In this case it is unstable, you see. Why is it unstable? Because 0.5 is positive. So the initial deviation from this level increases over time. There's a kind of instability here, and in fact our solution starts sufficiently close to this green one, but then it goes to a different, to a very different outcome, okay? So this is basically the meaning of the solution to this problem, in which we have term B on the right-hand side, which is not constant, it changes over time, and it is linear in this particular case. There are many more examples that we can solve, and some of them are in the slides, and I invite you to look at these examples and to try to solve them step by step. For instance, this one is very different from the previous one, because here we have a kind of stability, you see, because A is positive. Okay, no, this is constant, sorry. This is a constant case. This is again the previous example, don't worry about that. There are some repetitions in the slides. Okay. So look at the equation here. It is x dot plus x is equal to t, even easier. Okay, so the right-hand side is t. It's a linear function of t. Don't worry whether there is no constant here. It is just a linear function of t, okay? And the coefficient here is 1. In this case, A is positive, it is equal to 1. We will find a kind of stability here. Stability with respect to not to a steady state, but to some solution that changes over time. This is another way to solve it, I will show you later. But basically the solution that we can find with the same method as above is this one. Xt is equal to x0 plus 1 exponential of minus t plus t minus 1. Okay? So this is the very particular solution found with the method of the undetermined coefficients, like in our previous example. And t minus 1 is this one. Starts on minus 1 and it increases linearly. Okay? And this is the full solution. x0 plus 1 means x0 minus minus 1. So it is the initial deviation from the initial level of this particular linear solution. And you see what happens? There is a kind of stability here. Okay? So in the long run, our solution converges to this straight line. This straight line plays the role of a stable steady state. It is not a stable steady state. It is a time-varying trajectory. It's not a constant trajectory, but any other solution converges to this one. How did we find this solution? I can show you the method of undetermined coefficients applied to this case. Must be in the next set of slides. Otherwise, we will try to solve it here directly. Okay, here is it. Okay, here is the equation that we want to solve. X dot plus x is equal to t. There is one first method that I will show you later, which is called method of the integrating factor. But there is an alternative method, which is the method of undetermined coefficients, that consists of guessing a solution among a given family and then finding the parameters. So this is a very useful technique. Here there is here the description of how this solution method works. Now, I want to find a solution. Okay, I know what the general solution to the homogeneous equation is, okay? It is xt is equal to c times the exponential of minus t, okay? C times the exponential of minus a, which is minus 1, times t. Now, I want to find a particular solution to this among the set of linear functions alpha plus beta t. Its derivative with respect to time is beta. The function itself is alpha plus beta t. So beta plus alpha plus beta t must be equal to t. Okay? Beta plus alpha plus beta t must be equal to t. This is even easier. Alpha plus beta, constant term, plus beta t equal to t. Alpha plus beta must be equal to 0, because there is no constant terms here. And beta must be equal to 1, because the coefficient of t is 1, and the coefficient of t here is beta. So we have to match exactly the quantity on the left side to the quantity on the right side, okay? So alpha plus beta equal to 0 means alpha equal to minus beta, but now beta is equal to 1, so alpha is equal to minus 1, okay? Here are the two coefficients here, so it is minus 1 plus t, or t minus 1. This is the general solution to x dot plus x equal to 0, that is to the associated homogeneous equation, plus our particular solution obtained through the method of undetermined coefficients. Take the sum of the two, and this is the general solution to our model. If we want to find a particular solution, the particular solution is found in this way. We impose x at time 0 equal to x0. This becomes c minus 1, c minus 1 equal to x0. So c is equal to x0 plus 1. And this is why we find at the end, we find this one, x0 plus 1 exponential minus t plus t minus 1. Here there is a sort of stability property, and the stability property comes from the fact that this is exponential of minus t. So alpha here, a, parameter a here of the equation is positive. So this term disappears in the long run, and what is left is only the linear part of the solution, okay? But this is not a steady state, it is a time-varying solution. Okay, so this is another example. Okay. So what is another way to solve these models? The second way to solve this kind of models, my strong preference is on using the one just shown now, the method of undetermined coefficients. Okay, this is my preferred way of solving, because the other way implies the solution of integration by parts, which is, in general, it is longer, takes longer. It depends on which function you have to integrate by parts, but in general it takes longer. I mean, just to show you, if I want to integrate by parts this one, at plus b exponential minus gamma t dt, okay, it takes longer than just using a method of undetermined coefficients, okay? Anyway, we must find exactly the same solution. And let me show you how it works. I remember that we used the method of integrating factor to show you the solution formula of the basic case of constant growth. We used the method of the integrating factor, which is exactly the same. here, because x dot plus x equal to t, multiply both sides by the integrating factor, which is exponential of t. So in general, it is given by exponential of at, where a is the coefficient that multiplies x here, okay? If it was x dot plus 2x equal to t, okay, so the integrating factor would be exponential of 2t, okay? Now it is exponential of t. If I multiply the left side and the right side by exponential of t, I obtain this one. But this one is just the derivative of x times exponential of t. By the product rule, the derivative is x dot times exponential of t plus x times the derivative of exponential of t, which is again exponential of t. So this is the derivative of xt times exponential of t. And this means that if I take the integral of both sides, here I have the integral of the derivative of xt exponential of t, dt. And here I have the integral of this quantity. Now, this integral can be computed by parts. And this is just xt times exponential of t, okay? Because it is the integral of the derivative of a function, okay? So basically, this is probably the easiest integral to be computed by parts. The result of this is exponential of t times t minus 1. You can try this by exercise. So this integral by parts. So this is your f, this is your g prime. Exponential of t times t minus 1. So we have this. Now, we want to find xt. So multiply both sides by exponential of minus t, so that this disappears. Okay? So here we have t minus 1 plus c times exponential of minus t. So this is precisely the general solution that we obtain with the method seen before. Okay? If I want x0 to be x0, c is equal to x0 plus 1, and again we obtain our solution. Okay, so there are two methods to solve this kind of equations of this type. X dot plus plus ax equal to, unfortunately, not b constant, but p of t. Provided that p of t is a very simple function of time, linear or exponential. We have two methods to solve it. One is called the integrating factor. It is here. And the other one is the superposition principle plus the method of undetermined coefficients. Okay? So we have two methods. I suggest to use the second one because in general computations are much easier. Now, these were two cases with a linear function of time. Now I want to show you one case with an exponential function of time, which is even easier than this one. So let me, if you like, in the slides there is also an example where bt is quadratic. No quadratic bt in the exam, but I suggest to have a look at this because it is another exercise on the method of undetermined coefficients. Okay? So the principle is the same, exactly the same. Okay. This is a case with bt exponential. It is solved in two different ways. One is the integrating factor, and in this case it works very, it is just an elementary integral. There is no, when the right-hand side is exponential like this, we don't have integration by parts. It is an immediate integral, okay? But also the method of undetermined coefficients is easy. So let me start with the method of undetermined coefficient to solve this one. x dot plus 1/2 x is equal to exponential minus 1 over 5t. X dot plus 1/2 x is equal to exponential minus 1 over 5t. This is b of t. The principle is again the superposition principle. So first we find the solution to x dot plus 1/2 x equal to 0. Of t. Okay? And this is step 1. Next, step 2. Search among solutions of this type. This is an empirical rule which works perfectly in this case. Capital A, a constant, times exponential minus 1 over 5t. So remember here, keep the same exponent that you have here, but be more general, possibly multiply by a constant. If there exists a solution of this type, this is xt, okay, x particular of t. If there exists a solution of this type, x particular dot, its time derivative would be equal to minus capital A over 5, okay, times exponential minus 1 over 5t. Okay. Can you see that it is exactly the previous method, but now empirically, in practice, we know that when a function is like this, of course, we have to select a family of functions by imitation of the structure of the right-hand side. In the previous case, we have a linear, and we selected among linear functions. Now we have exponentials with this coefficient, and we select among exponentials with the same coefficient. And this is just because we want to be more general, okay? To have some degrees of freedom. Don't use capital A exponential minus a generic exponent times t, because it's too general, okay? It doesn't lead to the solution. Okay, so the time derivative is this one. So the time derivative plus 1/2 the function must be equal to exponential minus 1 over 5t. Okay, so this becomes minus a over 5 times exponential minus 1 over 5t, time derivative, plus 1/2 that multiplies a exponential minus 1 over 5t. So plus a over 2 times exponential minus 1 over 5t. This must be equal to exponential of minus 1 over 5t. And this means this is even easier than the previous case, minus a over 5 plus a over 2. Clearly, it must be equal to 1. Because there is a common factor here, which is the same that you have here. And this coefficient is minus a over 5 plus a over 2. And this must be equal to 1. Because only in this case, the left-hand side perfectly matches the right-hand side. So this means that, okay, so the common denominator is 10, minus 2, plus 5 over 10 must be equal to 1. Minus 2 plus 5a over 10 must be equal to 1. Okay? So 3a divided by 10 must be equal to 1. So a is equal to 10 divided by 3. So this is the solution. So our particular solution is 10 over 3 times the exponential minus 1 over 5t. So the general solution to x dot plus 1/2 x equal to exponential minus 1 over 5t is xt equal to c times the exponential minus 1 over 5 minus 1 over 2t plus 10 over 3 exponential minus 1 over 5t. Okay? If we impose that x0 is given, times 0 we have c plus 10 over 3. This must be equal to x0. So c is equal to x0 minus 10 over 3. Okay? So we put this x0 minus 10 over 3 here. We replace c with this quantity, and we have our solution corresponding to a given initial condition. And now that, we have a kind of long-run solution, which is this one. And since here we have a negative exponent, this part, which depends on the initial deviation from 10 over 3, which is the initial value of this solution, this part disappears in the long run. So basically the representation of this case is like this. Okay? So this is 10 over 3 times exponential of minus 1 over 5t, this one. If we start with a positive deviation, in the long run, this deviation vanishes and we approach this solution. Okay, so this part disappears in the long run, and what is left in the long run is only this part, which is called equilibrium solution. Okay, it plays the role of the steady state, but it is not constant. It is something that changes. It's a kind of long run trajectory, and in the long run, all other trajectories approach this one. And they approach this one because this is negative. Otherwise, we would be the opposite effect. Like in my first example. So this is a generalization of a steady state concept, which is called equilibrium solution, basically. Okay? And also these solutions can be regarded as stable or unstable, depending on this coefficient here. Exactly the same logic that we used for steady states. You can also solve this by using the integrating factor method. You start from your equation. First of all, please write the integrating factor correctly. Integrating factor is, here we have a coefficient which is 1/2, so it is exponential of 1/2t. Multiply the left-hand side by exponential of 1/2t. Multiply also the right-hand side by exponential of 1/2t. Here we are lucky, there is no integration by parts because it's the product of two exponentials. Okay, so they just have two different coefficients at the exponent that multiplies t. So the product of the two is exponential of 3 over 10t. But this is the derivative of xt times exponential of 1/2t. So when I take the integral of a derivative, I get xt exponential of 1/2t is equal to the integral of this. But this is an elementary integral. It's 10 over 3 exponential of 3 over 10t plus a constant. Next, multiply both sides by exponential minus 1/2t in order to make this disappear here. And you get 10 over 3 exponential of 3 over 10t times exponential minus 1/2 t plus c exponential minus 1/2 t. Again, here, take the sum of the exponents. It's exponential minus 1 over 5t. So basically, in this particular case, in this class of models, the exponential that you get here has the same exponent as the initial one here, plus c exponential minus 1/2 t, which is exactly our general solution that we found before. Next, if you like, you can find a particular solution, but it is exactly the same we did before, okay? So also the integrating factor method works here. So basically, the integrating factor method is, let's say, competitive in the solution of this kind of models if we have a time-varying BT which is exponential like this. I regard the two methods indifferent in this case, but if it is linear, the method-based, the heuristic method is much better and much faster. Okay, so this is basically the extension of our model to the case where BT changes in two very simple situations. Now, you have to remember one thing, just a curiosity. Does this method work? Is there any similar method for any type of function BT on the right-hand side? The answer is no. Only if the quantity BT on the right-hand side is a polynomial. We studied the linear case. In the slides, there is an example with a quadratic case, but there are no technical difficulties for cubic, exponential 4, exponent 4, and quartic, and so on and so forth. And only if it is exponential, only if it is a polynomial, and in some other cases that involve basically trigonometric functions. But there is no, I mean, the method in principle works in general, but there are no heuristics available to find the solutions, okay? So the method is general, that you have to take the sum between the homogeneous solution and the particular solution. That works, this is general, can be proven in general, but what we lack is the heuristics, basically, to find the particular solutions in cases that are more complicated than just the exponential of the linear one, okay? Basically, this is the basic problem, the basic issue with this method. Anyway, it is very convenient in the simple cases like this. Okay? Now, let me go back to a few more examples. Okay. Here is an example. These are easier, again with constant coefficient B. This is an example of unstable behavior in the basic case of constant coefficients. X dot minus 0.05x is equal to minus 10. Okay? So this is again the basic case. There is no time varying B here. What is, okay, since it is with constant coefficients, since this is an example with constant coefficients, it is easy to find the steady state. B over A minus 10 divided by minus 0.05, it is 200. So the steady state is 200. The general solution is xt is equal to c times exponential 0.05t. Remember, A is negative here, so we will have a positive coefficient in the exponent here, plus 200. and this is the general solution. If x at time 0 is equal to 250, then C is equal to 250 minus 200, which is 50. So the particular solution is 50 times exponential 0.05t plus 200. Okay? So basically the steady state is here. There is a positive initial deviation from the steady state, but since this is a positive exponent that increases with t, we have an exponential that explodes away from the steady state level, okay? If it starts below, we have something like this. It goes downwards with a trajectory which is again exponential, okay? So in this case, the steady state x star equal to b over a is unstable. So one of the most basic, really basic applications to economic dynamics is the dynamics of capital stock as a function of two different exogenous, let's say, two different forces. One is an endogenous force by which, without new investment, the capital stock depreciates over time. So if I, capital I, which is the investment flow, is 0, we studied this model already, it becomes k dot is equal to minus delta k. So this has a constant rate of negative growth, okay? But if we have a positive investment flow, then we can add, and the simplest assumption is that it is constant, we can add this constant I here. Of course, this is a linear differential equation with constant coefficients, because we can write k dot plus delta k equal to I, okay? This is our B, this is our A, okay? The steady state solution has a strong economic meaning and interpretation here. Why? Because B over A is just capital I divided by delta. So basically, the steady state level of the capital stock, assuming that the economy reaches an equilibrium in terms of the level of the capital stock of the economy, the steady state level will be larger. The larger is the investment flow, the larger will be the steady state level of the capital stock, okay? And the smaller will be the depreciation rate, the larger will be the steady state level of the capital stock, which makes sense, okay? Capital I divided by delta, the depreciation rate. The general solution is C exponential of minus delta t plus the steady state, capital I divided by delta. If we impose an initial level of the capital stock, next, k at time 0 is C plus I over delta must be equal to x to k0, okay? C plus I over delta equal to k0. So C is equal to k0 minus I over delta. So the initial deviation of the capital stock from its steady state level multiplied by my exponential of delta t plus I over delta. This is, since delta is a positive depreciation rate, this is something that in the long run will disappear, and in the long run the equilibrium level of the capital stock will be the one the economy reaches, okay, in the long run. For instance, depreciation rate of 2% per year, investment flow 2 units of measure, I don't know, per year, and it is the flow, of course. I over delta is 100, and this is the steady state level of the capital stock. Capital stock at time t is k0, the initial level of the capital stock, minus 100 times exponential minus 2% t plus 100, okay? So if this is 100, if we start below the steady state level of the capital stock in the economy will increase until it reaches its steady state level. we start above, it will decrease until it reaches its steady state level. Okay? So at the steady state, if you look at the steady state level of the capital stock, you have capital I over delta, and this means that at the steady state solution, if you multiply both sides by delta, you get delta times K star is equal to capital I. What is the meaning of this? The equilibrium in the economy will be reached when, if you apply the depreciation rate to a given level of capital, you have the loss of capital over one period, okay? So this is the amount the capital stock depreciates in one period, delta times kappa star, at the steady state. This is exactly offset by your new investment, okay? And this is the reason why the capital remains at that level. If you start below, it depreciates. The amount of capital loss in a period is smaller than the amount of the new investment, so the capital increases until it reaches the level of equilibrium. You start above, the amount of capital which is lost due to depreciation in one period is larger than your constant investment level, so the capital stock decreases until it reaches the equilibrium level, and at the equilibrium level, the two forces offset one another, okay? This is the basic interpretation. Okay, so this is just one among the many possible examples of linear differential equations with constant coefficients. And I would say that now we can just take a break. Okay, let's take a break and be here again in 15 minutes. Okay, we can start again. With a few examples on another type of equations, which is called separable. Okay, can you hear me? Okay, should be okay. Okay, so this is very simple examples of another type of equations which are called separable equations. Before doing that, I want to point out the meaning of the word autonomous equations. Maybe we discussed this already. But it is quite important in applications. So we have autonomous differential equations versus non-autonomous differential equations. And this is a concept that it's not related to linear or non-linear, it's a transversal concept, okay? So basically, a differential equation of the first order can be given a general structure, which is of this type. On the left-hand side, we have the time derivative of variable x. On the right-hand side, we have a mathematical expression that depends on both x and t, okay? We saw only examples of this general type, okay? For instance, x dot plus ax is equal to b is an example of this type, because it is x dot equal to minus ax plus b. So this is in principle a function g of xt, but there is no explicit dependence on t, okay? But it can be regarded as a constant function of t. Okay, this is an example of autonomous equation, because although the right-hand side in general is a g of xt, here there is no explicit dependence on t, okay? This is autonomous. There is no explicit dependence on t. Means no explicit. Now, we don't have to make mistakes about this concept. There is no explicit dependence on t. Of course, it depends on t because x dot is a function of x, and x depends on t. But this means it depends on t only through x. There is no direct explicit dependence on t. Okay, so let me show you direct dependence on t. Better to write direct dependence on t. It depends on t only through x. What about this one? X dot plus ax equal to 3t plus 1, plus 2x, for instance, equal to 3t plus 1. But this is a non-autonomous, okay? Because the dependence on t is both through x, because x is here, and you can move it to the right, it becomes minus 2x, okay? X dot is equal to 3t plus 1 minus 2x. Again, we have This is a g of xt, depends on x and t, and there is 3t plus 1 minus 2x, plus 1 minus 2x. There is both a direct dependence on t and an indirect dependence on t, okay, through x. So this is a non-autonomous equation. Okay, so autonomous versus non-autonomous means there is no direct dependence on t, or there is also a direct dependence on t. So this is the basic idea. Another example could be x dot is equal to minus 3tx. Okay? This is another kind of equation which is called, for instance, separable. And it features both a direct and an indirect dependence on t, okay? T times x of t. It depends on t and x. X dot equal to 3x. It is autonomous. This is non-autonomous. Clear? Okay, so it has nothing to do with linear or non-linear, because here you have a case of linear autonomous, linear non-autonomous. This is again linear in x, but it is a linear equation, but it is non-autonomous. This is a linear equation which is autonomous. This is, for instance, a non-linear equation. It's not linear, and it is non-autonomous. Why this one? This is autonomous and this is non-linear, okay? It is autonomous because you don't have an explicit appearance of t here. This is non-linear because x, it is squared here. This is non-linear because we have the square root of x, but there is also direct dependence on t. This is a non-linear and non-autonomous. Non-linear and autonomous, okay? Linear and autonomous, linear, non-autonomous. These are both linear and separable, and this is non-autonomous and this is autonomous. So there are very different types of classifications, okay? Different types of independent classifications based on different perspectives. And all of them are first order differential equations. First order means that only appear here the first derivative and the function. We do have also second order equation, third order equation. For instance, we don't deal with second order equation, but the second order equation would be like this. Okay, so you have a mathematical expression that involves both the second time derivative and the first time derivative and the value of the function and possibly a constant. This is a second order, in this case, linear differential equation. So we have many different types of equations. We only deal with first order. Okay, so let me show you a structure which is very simple to solve, which is called separable equations. It is simple to solve because it reduces to computing two integrals in general of elementary types, in our example of elementary type. The structure is like this. Remember that we have x dot equal to, at the right hand side, we have something which is g of xt, okay? G of x and t. But if our g of xt has this structure, it's not a g of xt, it's a particular case of that. It's a function of t times a function of x. It's a particular case of this general case, okay? x dot is equal to g of xt is a general expression for a first order differential equation. Now suppose that the quantity on the right hand side, which depends on x and t, has this kind of dependence. X dot is equal to a function of t times a function of x. Okay? For instance, x dot equal to 3tx minus x squared. Is this a separable equation? Can you reduce this one to something in which you have the product of two factors? One depends on t, only on t, and one depends only on x? No. There is a factor that depends on t, it multiplies this one, but then I could write x that multiplies 3t, but then minus x. So I cannot find a factor that depends on x times a factor that depends on t, and rewrite this in this way. Okay. Then this one, x dot equal to ax plus bt minus ax plus bt, p of t. This is not separable. Okay? But this one, x dot is equal to 3x divided by square root of 1 plus t. This is separable, for instance. Okay? Because it is of the type f of t times g of x. This is really important because if it is separable, I can do, suppose that you are here, if you divide by g of x both sides, on the left hand side you have something that depends on x, and on the right only something that depends only on t. Okay? So you can take two separate integrals, one with respect to x, one with respect to t on both sides, and then you have, in general, you have the solution there to your equation. So it works like this. This is the structure. These are two additional examples. This is separable, this is non-separable. Not separable. The solution steps are very easy, okay? So, if it is separable, you can easily separate the variables, which separating the variables it's also a common expression to say that we can solve two different problems separately, okay? You can separate the variables because you can divide by g of x, provided that g of x is different from 0, okay? If you divide both sides by g of x, you have x dot divided by g of x is equal to f of t. The left-hand side depends only on x, the right only on t. X dot is the time derivative, okay? So I write this, time derivative of x divided by g of x is equal to f of t, okay? So this is just the extensive notation. Now, what is the solution procedure? Computing integrals on both sides. So we have to integrate both sides. Now, be careful. Here we have x dot divided by g of x equal to f of t. When we integrate, the integrate of the left-hand side is 1 over g of x, integral 1 over g of x dx, is equal to the integral of f of t dt. If possible, solve both integrals. On the left, you have an integral with the integration variable x. On the right, it is t. Okay? Solve both integrals. And in general, by solving both integrals, you have something here that depends on x, something that depends on t, so you can solve for x and you get the solution to your equation, x that depends on t, okay? So you solve something that depends on x, something that depends on t, it's an equation, solve for x and you get the solution in general. Let me explain all the steps better, because here you may see that here there is some integration by substitution involved here, okay? Anyway, there are two main remarks. The first one is, if the equation is like this, and I want to write this like this, I must exclude the values of x here, I must exclude the values of x by which g of x is equal to 0, okay? Because otherwise g of x is equal to 0, and this doesn't make sense. But on the other hand, suppose that my expression g of x is, for instance, x minus 1, okay? What is the value that makes g of x equal to 0? It is x equal to 1. So if we have here g of x is x minus 1, x equal to 1 is a constant solution to my equation. Why? Because when x is equal to 1, g of x, that is x minus 1, is 0, okay? 0 times f of t is 0. So it's constant at the level 1, but its derivative will be 0, which is perfectly consistent, okay? So let me show you this example. X dot is equal to square root of t times x minus 1. I don't know what the solution, the general solution to this equation is, but I'm sure that xt equal to 0, identically equal to 0 for any t, which is a constant, identically equal to 1 for any t, which is a constant, okay, trajectory over time. X of t is equal to 1, constant, is a solution to this equation. Why? Because when xt is equal to 1, here we have 1, 1 minus 1 is 0, 0 times square root of t is 0 for any t. What do we expect about the derivative of a constant solution? It is 0, okay? So x dot must be 0. On the other hand, here we have 0, so the equation is satisfied. So basically what I mean is that before dividing by g of x, we must consider as solutions all the values, constant values of x, by which g of x is equal to 0, okay? So the first remark is this one. Before separating the variables, find the constant solution satisfying g of x equal to 0, because these are all solutions to your differential equations. These are all constant solutions to your differential equation, okay? Because next, when you divide by g of x, you cannot find them anymore. So you have to keep track of them initially, okay? Because when you divide by g of x, you cannot find them anymore, because now they are excluded from the solution to this differential equation, which is equivalent to this, except for those values of x for which this is 0, okay? Now you have this one, and basically, you take the integral of both sides here by removing the derivative here, or better, this becomes x dot, let me show you, it becomes x dot times dt, okay, which is dx. It is here. So we compute one integral with respect to x, the other with respect to t. So the second remark is that when we go from step 1 to step 2, in fact, we are integrating by substitution. Why? Because rewrite x in terms of t, okay? So this is x dot of t, or x prime of t, the derivative of x with respect to t, divided by g of xt, okay? Derivative of x with respect to t, divided by g of xt. And this is ft on the right. In fact, we are taking the integral of both sides with respect to t, okay? So this one, dt, and the integral of this one, dt. Now suppose that, make a substitution. If u is a new variable, which is x of t, what is du? It is x prime of t dt, okay? So this x prime of t dt becomes du. This becomes g of u, 1 over g of u du. And on the right side, we have integral of f of t dt. Now, we don't need to call the variable u, we can just call it x. So it's 1 over g of x dx, which is precisely what we get in step 2. But what is important is that you don't integrate here with respect to t, but with respect to x, which is our u in our standard notation for the substitution. So these separable equations is one very typical application of integration by substitution. So here, next, we don't even, I mean, it's not complicated to make the substitution here. It's just a matter of notation. But it is important to know what is the meaning of integrating with respect to x versus integrating with respect to t. Okay, we solve the two integrals. Here we get a function of t as the solution. Here we get a function of x, because we have this, 1 over g of x dx. Here we get a function of x. Here we get a function of t. And we solve for x. And we find, if we are lucky, we find the solution, x as a function of t. This is a very simple example. Next, I will show you two more, maybe today or maybe also tomorrow for a few minutes. Consider x dot is equal to a constant, alpha, any constant, times t times x squared. This is clearly separable because on the right I have an expression that involves x times an expression that involves only t. Now, before separating the variables, so dividing both sides by the expression that contains x, which is x squared, okay, I have to consider that when x is constant at the level 0, okay, so this quantity x squared is 0 when x is 0, okay? When x is constant at the level 0, on the right-hand side I have 0. On the left, since this is a constant function, has a 0 time derivative. So the constant solution x equal to 0 is a solution, a particular solution to our equation. Okay, get rid of this. This is already among the solutions. Get rid of this and divide by x squared, okay? X dot divided by x squared is equal to alpha t. Integrate, remember, if you integrate with respect to t, this becomes x dot dt, which is dx, okay? What is left here is just x squared in the denominator. So the integral with respect to variable x of 1 over x squared dx is equal to the integral with respect to t of alpha t dt, okay? This is an elementary integral if regarded as an integral with respect to x, because a primitive is minus 1 over x. Oh? And this is equal to alpha t squared over 2 plus c. Very easy, okay? So now we have that minus the reciprocal of our solution is equal to this expression that depends on t. First of all, I can multiply both sides by minus 1, so change the sign to both sides, okay? And I get 1 over x is equal to minus alpha over 2t squared. I could write minus c, but c is arbitrary, okay? C is an arbitrary constant at this stage, can be any number, so I can again write plus c, okay? We don't need to change the sign to the arbitrary constant here. I mean, it's not, if we change the sign, this is not wrong, but just write plus c because it is arbitrary. Now take the reciprocal, x of t is equal to the reciprocal of this one. 1 over c minus alpha over 2t squared. So this is the general solution to our differential equation. Okay? We want to understand how the solution looks like for a given initial condition and by specifying some numerical values for this alpha. Okay, Suppose that the initial condition is x0 equal to 2. X at time 0 must be equal to 2. What is x at time 0? I have to replace 0 here. It's 1 over c. So 1 over c, I want 1 over c to be equal to 2. 1 over c equal to 2. C is equal to 1/2. Okay? Go to the general solution formula, this becomes 1/2. So in the denominator I have 1/2 minus alpha over 2t squared. Okay, so my particular solution corresponding to the initial condition x0 equal to 2 is this one. Alpha is a parameter. I can multiply both numerator and denominator by 2. It becomes 2 divided by 1 minus alpha t squared. Now, how does this solution look like for specific values of this parameter alpha? If alpha is equal to -1, for instance, this becomes +1, so it's 2 divided by 1 plus t squared. It is a trajectory like this. Starts from 2, because the initial condition is 2 in any of these examples, and then it decreases like this. If alpha is equal, for instance, to 1 over 9, you put 1 over 9 here, and you get this very different trajectory. So if alpha is equal to 1 over 9, we have a very different trajectory for the solution to the differential equation. Okay, so this is not a differential equation, it is a family of differential equations because it depends on a parameter. But for different values of this parameter, we get very different types of solution, okay? So this is like this, for instance, it has a vertical asymptote here. Anyway, we have been able to arrive at the analytical expression of our solution, both general and particular, by just separating the variables and computing two different integrals, one with respect to x, one with respect to t. There is another example which is important for these separable equations. It is this one. I'm going to solve this example for you now. So this is, maybe I can get rid of this. Consider this one, x dot over x. No, x dot. This is already the second step. X dot is equal to 5%, 0.05, divided by 1 plus 0.02t, this is 0.05, okay, times x. Okay, by the way, is this an autonomous equation or is this a non-autonomous equation? Non-autonomous, there is a direct dependence on t. Now, the denominator, as t changes, the denominator is basically 1, okay? So as t increases, of course, it becomes larger than 1. But I could compare this one, which is 0.05 divided by something which is slightly larger than 1 for a long time, okay? It is very close to 1. I could compare it with x dot is equal to 0.05x. But in this case, we know how to solve the equation, okay? With x0 equal to x0, positive. In this case, what is the solution? xt is equal to x0 times exponential of 0.05t, okay? It is a constant growth model. This is very similar in practice, not so similar analytically, because now we don't have a constant growth model. We have to solve this model. Okay, so we write, so basically here we are saying that the growth rate is constant and it is 5% per year. Here we are saying that x dot over x, which is the time growth rate of variable x, is equal to 0.05. So initially it is 5% when t is equal to 0, but then it decreases very slowly over time. Okay? Can you see the point? When t is equal to 50, in the denominator you have 2, and this is 2.5%. Okay? So in 50 years, the growth rate decreases from 5% to 2.5% in a lot of time. Initially, it is 5%. How can we solve this differential equation? The integral. And again, we want to impose x0, x times 0 equal to x0 positive. Okay? The integral of 1 over x dx, okay, is equal to the integral of 0.05 divided by 0.02. This can be moved outside the integral, of course. And then, adjusting the constants here, 0.02 divided by 1.0.02 t dt. Okay? So this is basically 0.05 divided by 0.02 is 5 over 2. 5 over 2. This is the exact derivative of the log of 1 plus 0.02t. Okay? So the integrand is the derivative of of the log of 1 plus 0.02t. Okay? So here we have the log of x is equal to 5 over 2, the log of 1 plus 0.02 t plus a constant. Okay? And this means that, well, this can be rewritten as the log of 1 plus 0.02 to the power of 5 over 2. Okay? Plus c. So x is equal to the exponential of this is the exponential of this, okay? So it is equal to k, where k is the exponential of c, times 1 plus 0.02 t to the power of 5 over 2. Okay? If x at time 0, if I want x at time 0 to be equal to x0, time 0, this is 0, this becomes 1. So k is exactly x0, okay? Clear? This is the solution to this separable differential equation. But, I mean, this is, in fact, okay, looks very different from this one, because this is a power function of 1 plus 0.02t. Okay? This is a power function of 1 plus 0.02t multiplied by the initial level of the variable. But in the constant growth case, I have an exponential function of 0.05t. But they look very similar to one another, at least for the first period, okay? Because for the first period, both describe evolution with a growth rate which is very close to 5% per unit time, okay? In fact, if you go and try to plot them, you see that this one, which is the constant growth model, is the red one, okay? while the solution to our model with the same x0, which is 10 in this example, the solution to our model is the blue one, okay? It's not exponential, but for the first 10, at least for the first 5 periods, if not 10 periods, it is very close to the exponential growth. And in fact, the growth rate is very close to 5%. It's not constant because it tends to decline over time, the time growth rate, but it is very close to its initial level of 5%. Okay? So you see here the representation of the solution as the solution to a differential equation, starting from the specification basically of the growth rate in a case in which it is constant and another case in which it is time varying, but it decreases very, very slowly over time. It is, in the first period, it is almost constant at the level 0.05. And in fact, the two integral curves, the two solutions, look very similar, despite the different mathematical expressions, okay? But the main message is that we must be able to solve these simple types of equation. So basically, there is another example here that you may want to solve. But let me show you this example tomorrow. Now we know that the solution to this differential equation, is this one. How can we check the solution to a differential equation? By verifying, checking that this function actually satisfies our differential equation for any t. So we want that our solution satisfies the differential equation, which is like this, okay? So we want that our solution has a growth rate which is exactly as specified by the differential equation. Okay, so we want to verify the solution, and this is the last step for today's class. We found our solution x of t is equal to the initial level of the variable times 1 plus 0.02t to the power of 5 over 2. What is x dot? It is the time derivative. It is equal to x0 times 5 over 2. It is a power function. Times 1 plus 0.02t to the power of 3 over 2 times 0.02. What is the value of the function? It is this one, x0 times 1 plus 0.02 to the power, t, here there is a t missing, t to the power of 5 over 2. Okay, so this is x. What is x dot over x? It is this. Okay, so it is basically x0 and x0 can be simplified. Now we have 1 plus 0.02 in the denominator, because it becomes to the power of minus 1. So we get this is in the denominator, and in the numerator we have 0.05. So this function has the property that its time growth rate is exactly this one. But this is precisely what our differential equation requires. So with the differential equation, we have to find an unknown function having a time growth rate equal to this one. And in fact, we found this function, this family of functions, which actually do have a time growth rate which is equal to this one. So this is a way to check that our solution satisfies the differential equation. So what are the most important types of these separable equations for applications to economics, to finance? The most important types of these separable equations are precisely the ones in which okay, let me go again to the last page because it's much convenient to write. A separable equation is of the type x dot is equal to f of t times g of x, right? In my view, the most important types of these separable equations in economics and finance are the ones in which we have f of t here, but just x here. Okay? So a very peculiar type is this. Because this can be changed, it can be by dividing by x, can be transformed into time growth rate is equal to a function of time. Okay? Studying models and trying to specify the trajectory of a model in which the assumption is that the time growth rate is some time varying quantity f of t, reduces to a separable equation, which is very simple indeed, because when you integrate, you have on the right hand side the integral of f of t. On the left, you have the log of x, right? Because in general, they are positive variables. We have the log of x, so the log of x is equal to the integral of f of t, okay? So x is equal to the exponential of what you get on the right hand side. Clear? So this is, in my view, this is the most important and most useful type of separable differential equations applied to economics and finance. Okay, so try to focus on these types of equations. Tomorrow I will show you two more examples, and then I will show you a little bit of qualitative analysis of first order nonlinear differential equations. Qualitative means we are not able to solve the equations, but we can represent something that happens if we study the qualitative behavior to the equation. For instance, stability, instabilities, what are the steady states, what are the likely time path of the solution trajectories, and so on and so forth, without having the analytic expression of these solutions. This is called qualitative analysis. Okay, see you tomorrow. Tomorrow morning.